Hey calculus, here we are starting chapter 6. This is 6.1. We are going to be estimating with finite sums. I'm going to do this video in two parts. Estimating with finite sums. Okay, calculating distance traveled and doing the rectangular approximation method, which is known as RAM. Okay, so remember the hiker problem. Good old hiker problem. So in the first semester, we saw the connection between the slope of a tangent to a curve and the derivative of a function. Okay? They're the same thing. Or the velocity of the hikers. That was finding the velocity of a moving particle, which we're calling a hiker right now. Which is the central idea in differential calculus. This chapter, we're going to see the connection between area, and the area under this curve. So this is the slope of the curve. This is area under the curve, and this is going to be the distance traveled by the hiker. This is the idea of a definite. We've been talking about an indefinite integral. Now we're going to talk about a definite integral, okay, which is the basic concepts of integral calculus. There's a connection between integral calculus, second semester, and differential calculus. This is the fundamental theorem of calculus, and it relates the integral to the derivative, and it's going to simplify problems greatly. We get to that later on in this semester. Okay, that's just kind of a little intro. So distance problems. Suppose we're going to the World Series game in San Francisco. We travel 60 miles per hour for 2 hours. Okay, and so that's just rate times time, and we get 120. All right. So consider the graph of the velocity function. All right, so if we have our time, 1, 2, this is what in hours. And we have our velocity. Looks like we were on cruise control. This is in miles per hour. We're going 60. Okay, so the graph would sort of look like this. All right, so find the area of the rectangle here. Well, it's 2 by 60. What does this represent? The distance traveled. Same thing as the distance traveled. So we accumulated those miles. We accumulated those miles. So notice we had 60 mph times 2h. We accumulated miles, and it is the same visual as the area under the curve. Okay, so let's say our car had a velocity that was not on cruise control. So let's say our velocity looked like this. Okay, so right there. We didn't stay the same speed. The graph would no longer be horizontal, and the region under the graph would no longer be rectangular. So how do we find this area of an irregular region? I talked about this a little bit, alluded to this a little bit in class. Well, we're going to bring this vertical down and this vertical down, and we're going to partition the region into vertical strips. Okay? All right, so if I were to partition into 2, or 4, or 8, so on and so forth. As they get tinier and tinier, each little strip begins to resemble a rectangle. Just go like that, okay? Each one of these begins to resemble a rectangle. All right, so we are going to then accumulate all of those rectangles, and eventually with an integral, but right now we're going to estimate them with these rectangular with this RAM method, this rectangular approximation method. All right, the sum of the areas of the rectangles will give the total area. This is important. The total area represents the accumulation of the distance traveled for this particular particle, this hiker. All right, and you can always use the units of length and width of the rectangle to confirm, what cancels out should be what you're accumulating. So maybe it's not miles per hour, maybe it's, bacteria per minute, and this is minutes, and you accumulate the bacteria. So you can always be able to cross multiply here. The units do their dimensional analysis, if you will, and you should see what you're accumulating. Okay, so next page. All right, this is the good stuff here. So we have a pink elephant, okay, and as a velocity of t squared plus 2, where v is in feet per second and t is in seconds. How far does the elephant travel in 4 seconds? All right, so, and we're estimating. Certainly you could integrate up to position and then figure this out, but we're doing these are part of the AP curriculum, these approximation methods. And you need these when you have maybe a data table or when you can't integrate. All right, so let's plot our velocity graph. Okay, so at 0 I am at 2. All right, so at 0 I'm at 2. At 1, I am at 3. Okay, and at 2, I'm at 6. At 3, I am at 11. Right, and then last but not least, we had to go all the way to 4. At 4, I'm at 18. All right, so parabola. Okay, so there's my graph, and I want to bring down that boundary line right there. Okay, so if you were to go and put this on a t-table, we had 2, 3, 6, 11, and 4 was 18. There's a t-table for us. Okay, so let's partition this, and we are going to make rectangles using the upper left-hand endpoint, okay? Because we're creating rectangles from the left. This is a left rectangular method, approximation method, or an LRAM. This is an LRAM. All right, so we're going to go to this endpoint on the left. You start left, you draw right till the next endpoint and bring it down. All right, so you start on the left and go right. So don't get confused. A left rectangle starts to the left, but you actually draw right, and then you want to complete these here. Okay, so start left, down, complete the rectangle. Start on the left endpoint, over, complete the rectangle. So we have these 4 rectangles right here. Okay, so these rectangles are under the curve, so they are inscribed rectangles. Okay, so here we go. Now these are regular subintervals because they each have a width of 1. Okay, so we did regular subintervals. Sometimes they'll be irregular. These are regular. Okay, so the width of each rectangle is 1, and the height of each rectangle is the height of the function evaluated at the left endpoint. Okay, so the area of the first rectangle is going to be 1. Okay, it's going to be 1, and that height is 2. 1 times 2. The area of the second is going to be 1. They all are 1. They all have a width of 1, so 1, 1, 1. So this height is 2. This height is 3. This height is 6. And this height is 11. All right. So you could factor out the 1 and then just do the 2 plus 3. Yeah, that's going to happen here, so never mind. All right, so this is 1 times 2 plus 1 times 3 plus 1 times 6 plus 1 times 11. You can factor out that width and just do 2 plus 3 plus 6 plus 11. Okay, and you get 22. All right, so the sum of the areas here of the inscribed triangles is 22 feet. All right, 22 feet. All right, and so that's going to be inscribed. It's going to be less than the actual area because they're underneath. They're inscribed. Where am I? Okay, so the pink elephant traveled approximately 22 feet in 4 seconds. Okay, it's going to be an underestimate. Okay, so this was the velocity graph, so that was feet per second. This was seconds, so that cancels out to give us this feet. Even though area is square footage, when we accumulate, it's you want to cross multiply there to get the actual unit. Okay, so we're going to repeat the steps on this one, and we're going to do a RAM. Okay, an RRAM. Get a good viewpoint here. So we were at 0, 2, 1, 3, 2, 6, 3, 11, 4, 18. So now we're going to start at the right. That was 1, 3, 2, 6, 3, 11, 4, 18. So now we're going to draw these rectangles from the right. This is an RRAM. Start right and push them left. So like that. Like that. Like that. Okay, and over and down. Okay, so these are these rectangles. Seconds, my time axis. This is via t, which is our feet per second. All right, and because we are creating rectangles from the right, endpoint of a subinterval, this is called the right rectangular approximation method, or RRAM. These are above the curve, so these are circumscribed. Circumscribed rectangles, we colored or shaded that. All right, so the height of the each rectangle is the height of the function evaluated at the right endpoint. Again, these each have a change in x of 1. Okay, regular subintervals of 1. Okay, so the sum of the rectangles here. So we've seen that we can, if it's a regular subinterval, we can factor out that 1. And now the heights here are going to be, we're going to start here. So our first height is 3. Our second height is 6, our third height is 11, and our last height is 18. Okay, so this comes out to 38. So the circumscribed rectangles, this is going to be greater than the, remember this is the title of this is estimating. Okay, so we're estimating these sums. So the pink elephant traveled approximately 38 feet in 4 seconds. Okay, so we can see the actual distance is somewhere between 22 and 38. Okay, so somewhere between 22 feet and 38 feet. Okay, we are estimating, pretending like we don't know how to take that integral. I mean, you know, just so you can kind of get your head around this. Let's see, this was t squared plus 2. Okay, so we could do, you know, if you were to go up to position, this would be t cubed over 3 plus 2t plus c. And if you plug in 0, we saw that that's 2, so this c is going to be 2. T cubed over 3 plus 4, t plus 2. So this is going to be, if you were integrating, you would get, you put in 4 seconds, 4 cubed over 3 plus 2 times 4 plus 2. You would see it's the actual answer is 31. The actual feet traveled is actually 31.33. And this is how you would do it precisely. You would integrate up here, add C, got that initial point of 0, 2. If you plug that in, you'd see the C value's 2, and then plug in time 4, and so 31.33. So it certainly falls into 22 and 38, falls in between here. But you're going to run into situations where you can't integrate. You don't know how you're going to have to use. We have lots of different ways to integrate. This approximation one is when we run out of options in terms of doing something that has precision mathematically. Okay, so that is part 1, and I'll do the second part of this later on. Okay, good luck, guys. See you in class.